Say good afternoon to everybody. We're approaching the hour. I can see that we've got a fair few logged in now. My name's Ross Milne. I'm the current chairman of the Force Geophysics Network, and like to welcome you to this next in our series of webinars that we've been hosting since everybody's been in lockdown. And today we're very pleased to introduce Nick Huntbatch from Ikon Science. He's going to talk to us about anisotropy and how we can understand and account for that in our seismic analysis workflows. I guess anisotropi's been the sort of, in the past it's often been the elephant in the room that we've sort of quietly ignored, and I think we're slowly getting to grips with getting a better idea about it in lots of different aspects of geophysics. So the title of Nick's talk today is From Well Log Analysis and Correction to Well Ties and 3D Anisotropic Inversion. Just a little bit about Nick. He joined Ikon Science in 2008 and is currently the product manager for RockDoc software. And during his time at Ikon, he's held various roles from software to support, senior geoscientist and team leader within a QI team, and as the technical sales manager for Europe and Africa. His QI expertise includes rock physics, quantitative seismic well ties, seismic inversion, and seismic reservoir characterization. And he's also got experience with 4D rock physics and sim-to-size workflows. He's got global experience, having worked in many different hydrocarbon provinces around the world, including extensively in the North Sea, Norwegian Sea, and Barents Sea. And so Nick holds an MSci in geology and an MSc in remote sensing, both from University College of London. And before I hand over to Nick, there's just a couple of practical matters. I think everybody is muted at the moment. It's just a reminder to sort of stay like that. If you want to ask questions, you can actually use the chat button. There's an icon in the middle of the Teams meeting. If you want to ask questions that we can have time to answer at the end of the meeting. And I should just mention that this talk is going to be recorded and it will be available on the Force website after the talk. So with that, I will hand over to Nick. Welcome, Nick.
Thank you very much, Ross. Thank you for the introduction. And hello, everybody. Yes, so today I will be talking to you about anisotropy, specifically elastic anisotropy, and the potential impacts it can have on our subsurface prediction workflows and how we might be able to handle it better and therefore improve our predictions that we make. So let's see. Very briefly, we had that nice introduction, but I thought I'd show an image or two of ourselves just so you can get a better idea. Yes, my name is Nick and I'm the product manager for all QI applications across our product portfolio. And this PowerPoint or this presentation was actually put together by my colleague Kester Waters, who you may be familiar with, who is the Senior Vice President of Services globally for Ikon. And of course, we also have Rhydian Williams on the line, who is our Senior Business Development Manager for Norway and other regions. So that's what we look like for reference. But yes, so starting right at the beginning, why should we care about anisotropy in the first place? What actually is it that we're talking about? What methods do we have to be able to identify it and measure it? How can we calibrate our models? And then basically how it impacts various stages of the subsurface workflow. And of course, illustrating it where necessary or relevant with case studies is always a good idea. So, starting right at the beginning, basically, the impact of anisotropy, elastic anisotropy, can be seen throughout the workflow in many different places. And as Ross said at the beginning, often we ignore it for many different reasons, but there are cases when it can actually have a big impact on our workflows, the things that we do and the results that we generate, meaningful impact on further stages in the workflow down the line. So, when we're looking at amplitude screening, often anisotropy can lead us to see responses in the seismic, which if we don't think about anisotropy could mislead us into thinking there's something else. So we'll see an example of that later on, but it's basically, are we sure that we understand what's going on in the subsurface, what is driving the seismic responses? And if we don't include anisotropy, we might have a gap in that knowledge, which of course has impact on our amplitude screening methods. What we're talking about often with elastic anisotropy, of course, or mainly actually is the velocity, the impact on velocities, whether that's a measurement error in the well logs, so where your measurements are oblique to the bedding, if you like, you might get a measurement error, which is a speeding up of the velocities because of anisotropy. You know, and if you use those in things like depth time calibration, maybe if you had deviated wells, for example, it can give you significant error in that the measured velocities that you've got aren't actually the true velocities that you need. And that also goes through when we talk about our well ties. So of course, when we do a quantitative well tie, we are generating a reflectivity spike series from the contrasts based on the elastic logs, which we then use to have a look at comparing to our seismic trace and therefore hopefully estimate an appropriate wavelet. But if our reflectivity spike series are incorrect because our velocity log is impacted by anisotropy, then our well tie is going to be not correct, or it's going to have higher error or uncertainty associated with it. I'm sure we've all seen cases where seismic imaging has been adversely impacted by the processing steps that have been taken and anisotropy and how that was accounted for in the processing in terms of crispness of image, but also what angles relate, you know, what are the real angles we're seeing and the velocities that were used. And ultimately, when we get to the seismic inversion step, can we actually relate our isotropic models, which we generally calibrate? How do we actually extract isotopic properties from seismic inversion to put into our reservoir characterization workflow? And again, we'll see some examples of the challenges that we face at that step later on. And, you know, when we're at the field management stage and we're looking at things like wellbore stability and the geomechanical properties, again, it comes back to what are we estimating from inversion? Are we estimating something close to the truth, which we need to put into our geomechanical models, or are there errors because we're assuming an isotropic model, but the seismic is not responding, you know, it has that anisotropic element. So how does that impact on our understanding of geomechanical properties, which of course is crucial for wellbore stability, integrity, etc. So right off the bat, we can quickly come up with a fair few points where actually anisotropy could have a big impact in what we're doing. So specifically, what is velocity or elastic anisotropy? So basically, if a medium is anisotropic, basically if you take measurements at different angles, then your velocities will vary. So that can have two expressions. So it's either this idea of the vertical transverse isotropy, which is VTI, which is your layered earth, laminations, etc., your layering, or it's HDI, which is your fracturing. So basically, you know, fractures and carbonates, azimuthal anisotropy. So that's the two common expressions that we think about for geophysical applications. And that is described by Thomson's model, which basically has these 5 parameters to understand or explain or model the impact of anisotropy on velocities as a function of measurement angle. So you've got your 2 velocities in the direction of symmetry, and then you've got your 3 Thomson parameters being epsilon, gamma, and delta, of course. And at the bottom there, we have our equations, our model, which explain VP and VS as a function of angle with those parameters in there. So it explains how velocities change with measurement angle, essentially. Those parameters themselves are based on 5 stiffnesses, and those stiffnesses are described in different directions relative to the plane of symmetry. So in that case, in that image there, we have a layering anisotropy, a VTI type setup, and you can basically see that given those stiffnesses and the plane of symmetry, that each parameter has a contribution of P and S wave to it. So for example, with epsilon, you can see that we're looking at the vertical and the horizontal component of that. So as you move between the two, that's what epsilon is describing. And each of the other parameters has some contribution of the P wave and the S wave to that parameter. And those parameters, as I say, ultimately will is the model which modifies the velocities to account for that anisotropy. So that's how Thomson's model is defined and works, and the parameters, and it's one that we use to predict what will happen to correct our velocities in the logs, for example, but also to model seismic responses for that anisotropy, either VTI or HDI as well. So, you know, as pretty much everyone is aware, VTI anisotropy in particular is pretty ubiquitous. You know, we have layering in the earth, we have laminated shales, we have inherent layering geometry, which will give us a VTI responsible anisotropy. And often we tend to ignore it either because we think the impact will be too small to bother about, or equally, maybe we think that because it's everywhere, then it doesn't really have an overall effect, because if you look at a response from location to location, they both got the impact of that anisotropy, so we'll probably get away with ignoring it. But there are cases that we'll see in this presentation where it's not the case, that it's safe to ignore it and that it actually has a material impact on our predictions. It's safe to say that most commonly used modeling algorithms assume isotropy, so they're isotropic. For example, gas and fluid substitution assumes isotropic media. And indeed, when you get to seismic inversion, for various reasons, most conventional approaches, they assume an isotropic forward model. So within the inversion engine, when it's comparing the properties it's coming up with to the seismic, it's inherently in a conventional approach assuming an isotropic reflectivity equation in there, which we'll get into later why that's the case. So what we're going to do, focus from now on, because VTI really is the one we should initially at least think about most, is we'll be thinking about the impact of VTI anisotropy. So we need to have a think about how can we identify that this is at play, and how strong is the effect for where we're, you know, the basin, the rocks, the interval image test that we're looking at. How do we measure it, and how do we calibrate our models? So if we start on the left, we're at the kind of coarsest scale, you know, seismic acquisition, large scale layering. And within that, of course, there's a non-vertical component of the move out, which is this eta component. And so that should tell us something about anisotropy, and indeed we need to actually specify some parameters to do that. So the question at that step is, what parameters have been used to do that, and are they appropriate? You know, they should be based on analogous data. So if there are VSPs, etc., to come up with appropriate values for that component. And, you know, you need to, as a kind of an aside, it's very important to QC velocities, for example, from products that are going into a QI workflow. So basically saying, okay, so this is the seismic processing that we've got. What can we get to the assumptions that are made in the report, of course, but we should also compare the velocities that have been used to upscale velocities at the well logs to make sure that we've got a good match there, and that we haven't got some mismatch in velocities which are giving us flat gathers but are kind of being fudged to account for the anisotropy. Bottom left, you know, if we've got walk away VSP data, we can have a look at horizontal and vertical slownesses. So we have a plot showing that there, which will tell us something about our anisotropy, and indeed we can calibrate Thomson's model using that data if we have it. A more maybe pragmatic approach you see in the bottom right is basically looking at the well log velocity. So velocity logs, you know, sampled every half foot. If we have a range of deviation in our well bores, or indeed actually more correctly, if we have a range of different measurement angles. So you can see in that illustration there that of course the deviation of the well is at play, is important, but also the dip is also key. If we have that information, so measurements at varying measurement angles, we can plot that velocity versus that angle. And you can see here an example of that type of plot where we've got for P wave and S wave velocity data as a function of angle. And you can essentially then calibrate the Thomson's model to that data. So you can basically almost empirically fit your Thomson's model based on your observed log data. And of course, there's a lot of elements to that, things like making sure you take out the impact of compaction, etc., and doing it per facies, because as we'll see later on, and as is obvious, is that anisotropy is strongly related to facies, in that the level of anisotropy and the parameters will change on a facies by facies basis. So when we do at this stage this kind of calibration of the model, we need to make sure that we're taking into account facies, of course, and we'll see that later on when we get to the inversion, why this link between anisotropy and facies is key. Going down the scale to a finer scale again, we might even have some kind of laboratory experiments or tests looking at the velocities as a function of strain for the different stiffnesses, if you have that information. But essentially what we've got here is a variety of different methods to come up with parameters, and we can therefore, hopefully, depending on what information we've got, come up with a scale-dependent model for anisotropy. And of course, if all else fails, we've got other things to fall back on. So indeed, there's a lot of published information, published anisotropy parameters out there, so we can turn to the literature, and indeed even something more crude such as empirical relationships to velocity ratio, etc. So there are a number of different ways to come up with parameters to use in our modeling and our inversion, and there will essentially be scale dependent, so we need to make sure that we're using things at the right scale. So here, it goes without saying really that, of course, your core data is a very fine scale, point pieces, and then right up to your very large scale, broad layering of the Earth that you have in the processing, so the velocity move out analysis, etc. So that's kind of what we're looking to investigate and how we might actually understand where we get our parameters from. But if we go back to the actual subsurface workflow, which is really what the focus should be, is actually what's the material impact on what we're doing. We had a brief discussion about it at the very beginning here, but if we look at this slide, we start on the left in your more exploration setting, and you move through to production management, more mature setting on the right. So in an exploration setting, of course, we might think about seismic acquisition and planning that. So, are we looking at identifying fractures? So we need to maybe do a bit of modeling for HDI anisotropy back to our fractures, to say, okay, what's the best orientation to identify fractures or open fractures? If we're looking to improve the imaging on the far offsets, maybe we need to think about our Vti anisotropy and what were the processing parameters that were used. Of course, these days, anisotropic processing is kind of pretty standard, but it's a case, as I was saying, of understanding what parameters were used and where do they come from. Again, it should be from VSPs or other analogous information to do that. When we move through to our seismic forward modeling and amplitude screening, we should factor in anisotropy in the modeling. So, that's a case of understanding if we've got measurement errors in the elastic logs. Do we know what the true isotropic properties of each facies that we're looking at modeling is? Are our synthetic models that we're coming up with, the reflectivity, are they appropriate to compare to the seismic? We'll see more of that later on. Pore pressure prediction, of course, often based on velocities, and if those velocities are impacted by anisotropy, it could lead us to poorly calibrate our models, and also when we actually come to extract pore pressure from seismic velocities, we need to think about how the two relate, and so forth. As you go through all the way to production management, when you get to a more mature field, we're talking about geomechanical effects, wellbore stability, wellbore integrity. And again, a lot of the models that are used to do that are isotropic, and therefore, they're expecting or need isotropic inputs. So if we're not able to provide those, because the seismic is seeing that anisotropic effect, then we're going to have a problem with our prediction. And of course, that's not very good in terms of if our wellbore stability models are off, we can have all sorts of issues with non-productive time, etc. So obviously very important. So if we start with reference to that workflow on the left-hand side in a more exploration setting, this is just a nice example of how including an anisotropic case within the modeling framework can be crucial. So this is from a particular basin in the tertiary where many false positive amplitudes have been drilled. The West of Shetlands, it's kind of well known for AVO failures, I suppose, for want of a better term. But, that's for a number of different reasons, including undercompaction of brine-bearing sands, differential uplift, so where things have been uplifted from the deeper section into the shallower section where you don't expect them. But also anisotropy is at play there, so VTI layering anisotropy in the shale cap rock. And what we have on the right here are a series of half space or single interface AVO plots, and you start with the shallowest at the top left and you go to the deepest bottom right. So these are interfaces at different depths, and they're for brine and for gas bearing, and the solid lines are for the anisotropic shale above. So the dashed ones, the shale is isotropic, and the solid ones, the shale is VTI, so it has layering anisotropy in it. And what we can basically see that, when you include that VTI effect in the shale, you end up in pretty much every case blowing up the gradient. So the gradient becomes a lot steeper, which basically means that we change our AVO classes. So we might go from seeing, for example, in this case, we're expecting a class 2 for a gas response in the isotropic case. And then if we add a bit of anisotropy into a brine case, we actually start to get to responses which are very similar. So there's already, without even changing depth very much, a risk that a anisotropic shale over a brine sand will start to look more like an isotropic shale over a gas sand. So that's the kind of first obvious gotcha or pitfall. And then it gets a lot more confusing or dangerous, I suppose, when we've got this uplift happening. So when deeper, older rocks are uplifted into the shallower section, you can start to see responses which are associated with gas sands, but coming from a more diagenetically, more cemented sand with an anisotropic shale, having very similar responses. So yeah, again, it's understanding what the amplitudes are actually responding to, and if we don't actually have a clear understanding or more complete understanding of what's happening in the subsurface, then there's obviously a lot of risk of error and interpretation mistakes. Depth time calibration. This is a long offset lateral, so it's got high deviation out to 60 degrees in the deeper section. So basically, whenever you're looking at these highly deviated wells, you're going to want to be looking at anisotropy and the impact of anisotropy on the velocities. So specifically talking about the depth time conversion, basically, in these highly deviated wells, we often, or pretty much always, well, never, I should say, we never have the VSP data, check shot data, etc. And often we need to therefore rely on integrating the sonic or velocity log and hanging it off a horizon. And of course, if we do that in this case, we can see here that the black log in the VP track is the measured, and this red one actually, for reference, is the verticalized, or the true vertical velocity. So actually, if we didn't think about that and the VTI effect, we would actually have a two-way time uncertainty at target of around 150 milliseconds. So, it's obviously another case where, not thinking about anisotropy can impact our depth time conversions. And even where we do have check shot data, it's important to have a look at, is the velocity data impacted by the layering in the shales? And moreover, on the same topic, when we actually get to that well tie stage, we'll see here that Again, with this highly deviated well, we've got that 60-degree inclination into the reservoir section. We don't really know how to tie it because we don't have that robust depth time conversion. And if we just integrate the sonic, we have timing issues. But we also have issues in our reflectivity because the shale layers are seeing that faster velocity because of anisotropy. And you can see here in the image that this is the tie in that first seismic and synthetic track where we haven't done any correction. And essentially what you see is at the top of the target, there is effectively no well tie. You know, we're not modeling the seismic or matching it in any way at all. So obviously that's not great for us. We don't understand how to tie the well. Where do we shift it? Do we need to shift it? Lots of issues. And that's really because we see in the synthetic, it's pretty flat through the overburden into the sand. And that's really because, as I say, the contrasts have been changed by that anisotropy in those shales. Such that you can see here when we look at this is the acoustic impedance here, that it's a lot flatter going into that, and you just don't see that event. And as well as the timing issue, it leads us to have this well tie problem. But after correcting the velocity log on the right here, we can see we've much improved the tie. So the velocities have been corrected for anisotropy. The timing is improved because we've been able to do that integration of the velocity log a lot more robustly, and we can actually say, oh, okay, maybe we can tie this deviated well. So, you know, in this case, we're only focusing on anisotropy here. Of course, with deviated wells, there are many issues with the tie, but actually accounting for something like VTI can actually push us a long way down the path to being able to tie these wells more robustly. The other aspect, of course, is when we get to our inversion stage, we need to, of course, build a low frequency model in your conventional approach to give you the low frequency information. And what we have here on this section view is the wells that have been input to build that low frequency model, and the deviation, or the average deviation through the section, is posted at each well location. So you can basically see that, given everything's in about the same depth, that the inclination angle or the wellbore trajectory is having a big impact on the low frequency model that we're putting into the inversion, and therefore that will be pushed through into the inversion products. And if we look over on the left here, we can see some of that well data plotted up. So top left shows the VP versus the density. And given we're looking at velocity anisotropy or elastic anisotropy, you know, the density isn't sensitive to that, the velocities are. So what we have in this upper plot is the data colored by that inclination angle, and we can see a systematic shift where the higher angle wells have got a systematically higher velocity. So it's that measurement error, which we're actually injecting into our low frequency model, and therefore kind of biasing our inversion products, given that the low frequency model, of course, has a big impact on those kind of model-based inversions. If you plot the same data as a function, again, as we saw earlier, as a function of inclination angle, you can see that systematic increase in velocity, you know, out to 25%, 30% faster at the highly deviated wells than at the vertical wells. And, you know, again, you see that in the low frequency model. So a better approach, of course, is, as we talked about before, verticalize the velocity logs in the wells before you build the model, and therefore avoid this problem. You know, if you just push on through and just bring your wells in deviated or otherwise, don't correct the velocities, as I say, it can have a material impact on your predictions from inversion. So inversion is actually, of course, a big part of this. We focused mostly on well tie and a bit of modeling, but actually we need to think about how do we predict elastic properties from seismic, which is potentially showing the impact of anisotropy, or measuring that. How do we actually get back to the isotropic properties that we need for our models that we've calibrated? Because ultimately, you know, we need to predict properties and we need to relate it back to things like porosity, lithology, or pore pressure, even in a pore pressure workflow. So most inversion algorithms are isotropic, and that's really going back to this point that anisotropy and the anisotropic parameters are very much linked to facies. So they kind of have to be isotropic, because we can't distribute the Thompson's parameters before inversion. So we don't know how they change because the facies inherently aren't in those conventional inversion approaches. So there are some solutions out there to how we handle this disconnect between what we're looking to get out of it and what the seismic is actually measuring. So, you can adjust the wavelet scaling. So a bit of kind of a fudge or a scaling adjustment of those wavelets should help us capture that effect of anisotropy in the seismic. And actually, if you think about it, anytime you estimate wavelets from anisotropic seismic data, you're always going to see that impact on the scaling, whether you're consciously doing it or not. It's going to be inherently there. There's not much you can do about it. If you're using a quantitative approach, of maybe a Roy White type approach, you're going to see the impact on the scaling, which, we'll see an example in a minute, can help us to a degree to get better properties out of inversion. Another way that's quite interesting, we'll have a more close look at in a second. It's quite an interesting concept, is the idea that, okay, so we can't necessarily handle it in the reflectivity equation in the inversion, but if we come up with these pseudo isotropic properties, elastic properties, basically by adjusting the elastic properties that therefore will then account for the anisotropy, we can have an isotropic equation, but it inverts for these pseudo isotropic properties. So it's basically shifting the impact into the elastic logs rather than accounting for it within the reflectivity model. Which we'll have a look, as I say, in a minute more closely, but it's a clever approach. But we still need to construct those pseudo isotropic logs at the beginning. They basically take the Thompson's parameters and adjust the elastic logs. We still need to make that low frequency model. And actually, if you think about it, what we get out of the inversion will be pseudo isotropic logs, which aren't the ones we need for our modeling, really, and they're actually quite difficult to interpret in terms of what they mean. We'll look at it again in a few slides' time, but a better approach, of course, is to understand that anisotropy, as I say, is related to facies. So inherently, the inversion needs to know about facies, and therefore we can then in a prior sense, say that, well, give each facies a set of Thompson's parameters based on our modeling and measurements, and therefore the inversion itself actually includes anisotropy in a anisotropic reflectivity equation. But we'll have a look at that later on. So this is to set the scene for inversion, I suppose, an example of a vertical well offshore Malaysia. And it's basically showing isotropic synthetics and anisotropic synthetics. So we have an anisotropy model here. These are the parameters as they vary, of course, into the shale or shaly sections. That's where you get the bigger numbers. And if we look at the difference, which is a straight subtraction, we can see that in the near angle case, there's not a lot of difference as you might expect, but as you build out beyond 30 degrees, you start to see big changes. So it's really your VPVS ratio and density term which are being impacted here. So, the amplitudes, they both increase as you go out, but they also dim as well. So depending on which reflector you're looking at, it's not just the case that everything is getting brighter because of anisotropy. In some cases, things might be dimming, the gradient is going the other way, which kind of goes back to what we were saying about using these wavelet scalars, which, because it can dim and brighten with offset, your scaling adjustment isn't always going to be able to handle that. It's more complicated a response than can be handled by simple scaling. This is the idea of using these pseudo-isotropic properties. So you'll see there we've got in the first reflectivity equation is the Ruger equation, which basically is an extension of Aki-Richards to account for anisotropy, and it does that through incorporating the Thompson's parameters that we discussed at the beginning. So, that's fine. It basically says if you've got contrast in those parameters, that's how it will impact the reflectivity. And, easy to use on your forward model. You just have to build that anisotropy description or set of parameters per facies, as we talked about, and then plug that into the reflectivity equation, and you've got your synthetic. Not so easy in the inversion, of course, because of that facies element. We don't know how to include or distribute the variations in Thompson's parameters within a conventional type inversion. So this is this Van Riel and Debye method, where basically they come up with kind of isotropic equation. It doesn't have that element of the Thompson's parameters in it, but what it does require is that we adjust our elastic properties given the anisotropy parameters such that the impact, we can model the seismic response by relating it back to these pseudo isotropic properties. So in that case, we have an equation we can use in a conventional type inversion, and it will invert back to pseudo isotropic properties, but it will actually explain the seismic response correctly, rather than just assuming it's isotropic and having that mismatch. So if we have a look at what we are actually generating with that equation in terms of the pseudo isotropic logs, we can see that the AI is pretty much identical, or it is identical, but it's when we get to the VPVS, you can see that actually where you've got the anisotropy in the shales, we have to boost up the VPVS ratio. So where we see the deviation between these logs is VPVS ratio between isotropic and this pseudo isotropic method. So in order to account for the anisotropy in the seismic, the effect, what's happening here is that the elastic properties, the VPVS, is being in the shales bumped up, and for the density term, you can see it's actually dropping significantly. So the normal density is where I've got my cursor, and then the pseudo isotropic in the shales is dropping right down, again to account for that. And we can see the same AI VPVS ratio and density upscaled over here. And when we actually model it, so we take the isotropic logs and we put it through the Ruger equation given our anisotropy model to make a gather, we do the same with the pseudo-elastic properties and the pseudo-isotropic reflectivity equation, and we pretty much got no difference. So, it works in terms of matching the seismic response, but actually if you wanted to interpret these logs, it's not so easy, especially, for example, with the density, where actually, if you look at some of these sandy sections where you've got a change in the character of the density completely. So as you'd expect, more physical, or a drop of density into the sand. Actually, after the correction, you get a flip of that where it actually increases into the sand. So it's kind of disconnected from physics, I suppose, if you like, but also what a geologist would like to interpret. It doesn't really make sense in that world anymore. And of course, we still have to always think about what we're going to do with these impedances. If we generate them from seismic, what models are we going to use to relate them back to what we're actually interested in? So do we need to do our rock physics modeling, our classification based on the adjusted logs, and how does that work? Do we have to convert these pseudo-elastic properties back to the correct logs for that? So a lot more work involved. This is actually running some of these inversions on this as a kind of synthetic on this well here. So starting at the beginning, what we've got is tracks here where you've got AI, VPVS ratio, and density. So 4 inversions, and just having a look at what comes out of them. So on the left, isotropic seismic, isotropic inversion method, and isotropic wavelets. And we're, as expected, given this is synthetic, noise-free, we're getting back to pretty much what we put in. That's fine. What we might then do is actually say, okay, what happens if we had some layering anisotropy in our seismic response, but we didn't account for that in the inversion or the wavelets? Of course, this isn't a realistic real world case, because as I say, the wavelets themselves, if they're estimated from the seismic data and it's anisotropic, they'll always to some degree capture that. You wouldn't have purely isotropic wavelets with anisotropic seismic if you're using a quantitative well-tie approach. But what happens is, if you ignore it, basically the anisotropy effect, you start to overshoot your VPVS ratio, and the density, of course, is basically flipped polarity. So, you're not accounting for what the seismic is responding to correctly, and therefore your predictions are not great. So we can do something. We can, as I say, optimize our wavelets with scaling. We can try and massage things to look a bit more sensible, and that inherently happens really in practice. Even if you're totally ignoring anisotropy, it'll just happen by default almost, without thinking about it. And on the right here, we've got our clever bit of maths where we have come up with these pseudo isotropic elastic properties. And you can see we're doing a good job there. So it's matching the input from the inversion so that's great. But again, these logs aren't our isotropic logs. So you can see things like the density going up into the sand, etc., etc. So yeah, it works perfectly, but it still has challenges, and the results aren't quite what we actually want. So I think it's safe to say that apart from the perfect isotropic one, none of the proposed schemes really get us to where we need to be, which is those true isotropic elastic properties. Which is basically where we come to in saying that what we need really is the facies to be included, because as I say, without having a knowledge of the facies and the inversion, we can't properly relate the isotropic properties to the anisotropic seismic response. So what we've got here is a example, again, another little model toy. You've got your truth facies here from the log data. This is your isotropic inversion. So it's basically essentially saying what you can invert from that data, how close you can get to the truth. And then on the right, we've got our, well, in this case, we've dropped the pseudo isotropic case. But what we do have is ignoring it completely, which is this one where my mouse is. And as I say, that's probably not a realistic scenario because of the wavelets would never be, they'd always be to some degree catching the effect of anisotropy. And, given that you've got oil everywhere there, you would at least have some concerns about the response and say, hang on, something might not be right. So potentially an obvious one to spot. If you did adjust your wavelets, or inherently, as I say, you probably would have done already, by default, we come up with a response which is closer to our water-wet model, but actually, because of that not capturing the gradient correctly, the VPVS ratio, we are seeing a isolated oil-bearing sand there, which actually might look more realistic. So you might say, okay, I've done a good job here, I've adjusted my wavelets correctly, and I'm coming up with quite a nice little perspective interval. But actually, it would be a complete misnomer, which is coming out from the fact that still we haven't captured the impact of anisotropy correctly. So on the end, we've got a facies based inversion where we've included per facies Thompson's parameters, and the forward model within that inversion is actually the Ruger model. So we do the calibration, as we said at the beginning, based on the various data types we've got. We, in our prior facies model, which goes into the inversion, it's a Bayesian sense, so it has a prior model per facies elastic properties, and they can also have Thompson's parameters. So what it basically does there is it says if it's classifying one type of shell, it will give it a specific type of Thompson's parameters or set. Another shell will have a different type, and sands, generally speaking, will say are isotropic, given that we're focusing on VTI here. And that basically allows it to model the interfaces that the seismic is responding to in a much better way, and ultimately come up with a facies classification with these brine sands in blue, and the green is the oil sands, which is pretty close to what we get out of the isotropic seismic isotropic inversion. So, if we really want to pose the problem correctly for inversion, we inherently have to understand that anisotropy and the parameters are facies dependent. So if we don't have a concept of facies in the inversion, there's not really any way we can get back to what we need to get back to. So last couple of slides now, it's just basically a bit of a, yes, we focused on the rock physics part and the inversion, the QI part, but where do we send these products? What are they used for, and what are the impacts that they can have on drilling decisions and all that key stuff? So this is another, in the same vein as the last one, actually, where an inversion is being run on a synthetic data set, assuming isotropic seismic and an isotropic inversion, but with an anisotropic seismic, and then anisotropic seismic and anisotropic inversion. So what we have here is the blue is our isotropic case recovered using an isotropic inversion of isotropic seismic data. If we ignore that anisotropic, or we have that anisotropic element in the seismic, but we ignore it in the inversion, we come up with the red trace in here. So this shale cap rock actually has got strong VTI, and for this synthetic inversion example, the seismic that's going into the inversion has included that strong anisotropy, but the inversion itself is actually ignoring it. So what happens is, in terms of VP, we actually get around about 250 meters per second difference between what's predicted and the truth at the top of the sand there. And there's also included, for reference, a purple color, which is actually the anisotropic input seismic data, and then anisotropic inversion. You can see we get back pretty closely to the blue. So what we're saying here is that if we take this into our understanding of pore pressure and cap rock integrity, etc., we can see there's significant risk of misunderstanding what we're going to encounter with the drill bit. 250 meters per second, not insignificant in terms of those workflows. And if we look at another case in the same vein, this one not including inversion, it's just looking at the velocity and the pore pressure prediction. If we didn't correct our velocities for VTI or layering anisotropy, we come up with a pore pressure prediction, which is not close to the truth by a quite significant margin. So of course the velocities are faster because of anisotropy, which makes it look like it's not so high overpressure or lower pore pressure, and therefore our model starts to diverge quite significantly from the actual corrected one. So the red is the corrected vertical velocity, and you can see you have a significant difference in the prediction of about 2,175 psi, which obviously is fairly significant in terms of pore pressure prediction and what you the error range that you need for your well plans, etc. So again, not including this effect will have significant and serious impacts, or could do, on your pore pressure predictions. So that's more or less everything I wanted to share with you today. But to wrap up, everyone's aware, I would say, that anisotropy is ubiquitous, that it's everywhere. Inherently, it has to be, given the nature of geology and the layering of rocks. But we don't necessarily just have to ignore it, because there are many different ways to measure it, to understand it, to calibrate our models, whether that's simply referring to literature, or if you do have VSP data, etc., but even looking at seismic processing, and of course a more empirical approach, which is often quite useful. If you do have that analogous well data with varying inclinations, it's not exactly a onerous task just to plot that data up, velocity, density, and then color it by inclination as a kind of first pass. If we can just do that, then it will already start to tell us something about the anisotropy, and if it's present. And we need to be able to understand the impact on the workflows, because as we've seen in some of those examples, both in terms of understanding what amplitudes mean, understanding our predictions from seismic data, whether we've got a hydrocarbon bearing response or not, whether it's pore pressure predictions or wellbore stability, it can, in certain situations, have a real material impact on what we're doing. So don't ignore it, but we need to actually use it to our benefit. We need to use it to get better predictions in the subsurface. So hopefully that was interesting for everyone, and I'll finish there, but I guess if there are any questions, I can take them now.
Okay. Thank you very much, Nick. That was really interesting and timely. If anybody would like to ask a question, there's a little button you can press that says raise your hand, which we haven't tried before. There's nothing in the chat, I don't think. So does anybody in the audience have a question for Nick? And I guess we're at the sort of critical mass of number of people here. I had a few questions of my own. Oh, we have somebody who pressed the button, I think. Andy. Would you like to ask a question, Andy?
Hi, Nick. Can you hear me now?
Yeah.
Yes. Hi, Nick. Thank you so much for a great presentation. I really enjoyed that. I was wondering if you can help me with a query. I mean, anisotropy can be measured at different scales, as you suggested in one of the slides. We can certainly measure anisotropy whenever we evaluate processing or even at the log scale. But surely in my mind, as I see it, I mean, the result from that from different scales will introduce biases in any analysis we do henceforth. What I mean by that, I mean perhaps if we introduce anisotropy measurements from processing into our inversion, results will be different as well as use results from observations from wet logs. So my question is how do we handle that? How we can account for the fact that we are dealing with the scalability issues, if you like?
Yes, absolutely. You're absolutely right. Yes, if we look at different scales, we're going to be measuring slightly different things, of course. So we need to make sure that we're applying the measurements that we take to the right problem, I suppose. So if we're looking at the verticalization of log data, then deriving the parameters given those, as I was mentioning about that empirical approach, or with VSPs would probably be appropriate. And equally, you might not necessarily want to apply those parameters to your processing because again it's seeing a coarse layering and a different type of anisotropy. So I think the first thing is to make sure that your scale dependency of your model is appropriate for what you're trying to do. So when you get maybe to the inversion, maybe looking at the ones which were used in processing might be more appropriate, or somewhere in between, maybe with the VSP. So I think the key point is to just tailor it to what you're trying to achieve, whether it's correcting the velocity logs for that Vti anisotropy, or whether it's putting them into the inversion. But yeah, you're certainly right that it will have an impact on those parameters because it's inherently measuring a different thing.
All right, thanks.
Okay, was there anybody else in the audience? I guess I had a couple of questions myself, Nick. I'm sort of working with seismic processing, so that's kind of what they're related to. When it comes to anisotropy, I think it's actually it's still a bit of a struggle to get to kind of come up with some parameters with any confidence, and so I always get a bit nervous when I hear someone say, they assume that was done right.
Yeah.
So I was just thinking, like one of the kind of logical places to QC that is if someone's going to end up doing inversion or some of the work that you've just shown here, and I was wondering if you had any sort of good tips for how we might include something in the QC that sort of allows us to check that whilst we're doing it in your domain, rather than waiting for us to hand the data over.
Yeah, I mean, absolutely. So yeah, just first up, I suppose, my expertise, if you like, are in the QI type of things. I'm certainly not an expert on processing, but it is things like making sure that the velocities match at the wells. So the velocities that are used in the processing are consistent with upscaled velocities at the well control, because that's something that I've seen in the past where they don't match up anymore because the velocity has been adjusted to account for essentially the impact of anisotropy. So kind of correcting it by changing velocity, which of course gives us all sorts of issues in QI. And other things is, can we use VSP data? I suppose, is any VSP data available to have a look at walkaway VSPs, etc., to try and come up with a sensible starting point. But I guess a lot of it also comes down to the quality of the imaging, etc. So there are many aspects to it, but from a QI perspective, yeah, it's certainly about making sure the velocities are correct, and even running test inversions to see if you can recover what the ties look like, basically, in terms of the inverted impedances at wells.
Yeah.
So yeah, not straightforward.
Okay, thanks. I think I missed as well, just a question towards the end when you were talking about anisotropic seismic versus isotropic seismic. Are you just referring to how the sort of the velocity has been treated in the processing, and because that has more of an impact on the depth thing more than anything else, right? Or is there something else that you see as a difference there in terms of average?
Yeah, I mean, I was just kind of referring to the quality of the imaging. Also, yeah, how obviously we get to how do we flatten the gathers, basically? How are the corrections done? So when you have that eta term, for the non-vertical move-out component, what are the parameters that are assumed there, and are they appropriate for the actual rocks? So it's basically, how do we get up with a crisp image which has flat gathers? You know, what are the velocities that are assumed, and what are the parameters that are assumed, and are they consistent with the measurements that we have at various scales?
Yeah, okay.
Scale, I should say. I guess otherwise, you know, if people do have questions, they can feel free to email me. If they've shared, are you sharing my email address? I don't know.
We can. It's not coming on the Force website. I think yeah. I guess they can look you up on LinkedIn, right?
Yeah, of course.
Just somebody's asking a question: will we get access to the recordings? And I don't know if Lynn is still with us. I'm not sure where they're going to be published, if it's on the Force website, which will be open to everyone, or on Basecamp, which will be Force members only. But
it's going to be posted on force.org on available presentations. So I'll send you guys the link, and should be quite easy to find.
Okay. That's great. So if there are no more questions, I'd just like to say thanks again, Nick. It was a really interesting presentation, and thanks for taking the time out to join us. And thanks to all of you who joined as well. And see you at the next one. Just watch out on the Force website.
Thank you.
Okay. Thanks.
Thank you.